Hello, everyone. I'd like to welcome you to the Critical Materials Innovation Hub webinar series designed for and by CMI. I'd like to tell you a little bit about our webinar today. First off, again, I'm also welcoming you from the Rockies. We're at Colorado School of Mines, and it's a gorgeous fall day here in the Rockies. If you have a suggestion in the future about a webinar, please, we'd love to hear your interest because these are designed for you, and we want to present things that are of value to you. This is a public webinar, and it's going to be available next week at aimslab.gov/CMI. We also have a YouTube channel, so if you go to the Critical Materials Innovation Hub, you'll also be able to see it there as well. Questions. We are going to be using the Q&A function, and we ask each of you to the questions are going to be held to the end of the presentation, but as you have that question, if you would put it in the box, we'll be queued up and ready to answer some of those questions. So again, that's going to be answered during the following of the presentation. I'd like to introduce our speaker today. If you want to forward that, thank you. Dr. Roberto joined Newmont Corporation in 2012. He's a processing director for the technical services and metallurgy function. And he's corporate CME for the biohydrometallurgy and supports early stage projects and sustainability activities. Before Newmont, he was actually, he directed and executed biotechnology and R&D programs at Idaho National Lab. And these are in the areas ranging from bioleaching of metals to biodefense. So a great background to present to us today. And I'm going to ask you, Frank, to take it from here.
Thanks, Cynthia.
You're welcome.
Good morning and good afternoon to those of you in the U.S. Whatever time zone you're in, if you're farther afield, welcome and thanks for joining us. I appreciate the invitation from CMI to present today's webinar, which is a recap of an article that I was asked to write with a colleague for The Bridge, which is the quarterly publication from the National Academy of Engineering. So perhaps you've read that. There were a couple of articles in that special edition on critical materials that focused on circular economy and recycling. When we wrote this article, I actually put a question mark because I think it's always a challenge in the United States to talk about recycling and circular economy. And certainly in the mining industry, it's very difficult when you're trying to make money to consider what else can you get out of your mine tailings, for example. But before I go too far afield, I did want to make a disclaimer that Newmont is a primary producer of gold, silver, copper, lead, and zinc. So we really don't have a business interest in critical materials other than copper at the moment, and certainly not for lithium. So just in case any shareholders are on the line, I am not announcing any change in business direction for Newmont. So please keep that in mind. I'd also like to acknowledge my co-author, Rob Dunne, who used to work for Newmont. He used to be director of metallurgy, and he is currently in private consultancy in Perth, Australia. But Rob is really a master of mineral processing. He was a co-editor of a recent 2-volume edition in mineral processing from the Society for Mining, Metallurgy, and Exploration. And just last week, he helped conduct a short course on mining and refining of EV battery minerals and manufacturing of battery cells. And if you were at IMPC, which is the International Mineral Processing Congress, there are also a number of other sessions that focused on the topic at hand. So if you were there, great. I wasn't actually able to go since I had some competing meetings to go to, but definitely the proceedings would be worth looking at as we consider how to make these metals more efficiently. So this is the article here. Call your attention to it. You can get any details that I might forget as I go through the presentation, or maybe even consider some other questions that come up. I did not put my email in here, but it's very simple, frank.roberto@newmont.com. So please feel free to contact me if you have questions after the presentation that don't get addressed during the Q&A. So from a mining perspective, it's all about where the metals are. I work for a hard rock mining company, as you might guess from the metals that I described. And when we look at mining, it has to be a global activity. We don't get to pick where the metals are, and we do a lot of exploration. Mining companies spend millions, hundreds of millions of dollars individually on exploration in many cases to find the areas where the high grade deposits exist. And this gives you an idea of the lithium producing countries. I'm sure everybody's familiar with the fact that a lot of our lithium is coming from brines, and there's something called the lithium triangle. I don't know if my mouse shows up for you or not, but if we look in South America, the countries of Chile, Bolivia, and Argentina make up the lithium triangle, and it's primarily recovering lithium from brines as lithium chloride. And then that has to be converted to lithium carbonate to make the primary lithium compound that's used in making batteries. Something to really look at, if you look at the dark colors, that's where uh, different amounts are produced. And you can see that Australia and China are also the largest producers, largely because they have large deposits of spodumene, which is a lithium aluminum uh, salt of those various metals. And lithium makes up a big quantity, 3 times the amount typically that's found in brines. And another big difference is that um, in order to get the lithium from that hard rock deposit, you have to crush those rocks and then produce a concentrate, which is typically what's shipped around the world as the product from hard rock mining of spodumene. So you can see kind of the quantities that are produced there around the world. And if you look at the United States, you can see that we are definitely not a major producer of lithium at the moment. And something to keep in mind about that is that it's going to take a lot to make the U.S. a major producer of lithium, and I'll show you something about that in a moment. But I did want also, in the contrast between recovering lithium from brines and recovering it from a rock resource, besides the energy intensity, the equipment, the energy to turn crushers and mills in order to crush and then recover the spodumene from hard rock. Another big difference with brines is that it's very water intensive if you're recovering lithium from brines. And you can see that it's been estimated that it takes 1,900 tons of water to get 1 ton of lithium. And you can imagine if we're talking about South America, if you've been to the Atacama Desert or know of it, then you know it's a very dry climate. And that amount of water really makes it challenging to recover lithium in those environments. And so one also has to consider not just energy intensity in terms of how that impacts the CO2 equivalents required to produce lithium, but then also the water and how that impacts the environment, the local communities who are already challenged for the water that they use for human purposes, and then uh, the balance between what the communities are required to live and then what's required to produce this important metal. So it's definitely challenging to consider primary production of lithium. And in the end, I think one lesson that I've learned, you saw that I spent a number of years at the Idaho National Lab, but going into industry, it's all about making money. So whatever resource you have available to you, ultimately, when you develop the flow sheet to recover the metal, has to be profitable. And that includes not just the cost of energy and water, but includes how far away you are from supply chain depots like transshipment ports to move concentrates of the metal from where it's produced, the energy required to move trucks and pumps in the operations at your mine site, and then global commerce. So all of those things factor into the profitability of a particular potential operation. And mining companies are pretty conservative when it comes to considering what a new mine will look like. So um, the cost and the price of the metal that you're selling all come into that balance, and we'll talk about that in a minute. So I did want to focus just briefly on, we hear more and more about how the US can become self-sufficient in terms of lithium. And I have a little bit of a difficulty accepting that. I mean, this is a USGS digital map of the sea horizon. So this is the area of soil just above bedrock. And if you looked at the higher levels of soil across the United States, you see very similar concentrations. But the thing to note here is that we're looking at lithium concentrations, though that dark red is 46 to 280 parts per million of lithium. So it does, these kind of maps do tell you where you're likely to find lithium, but whether it's economically viable to mine that lithium is another question. And I think I would say that right now there is only one commercial operation in the United States. It's operated by one of the big players in the lithium global market, that's Albemarle, and it's coming from brine. So that's Silver Peaks mine in Nevada. So if you look at this map, you can see, okay, there's a viable commercial mine here in this red zone. But that doesn't mean that across the United States, the nature of the lithium and the concentration is economically viable. One thing about brines is that um, I'll be talking about the economics in this a bit, but you have to evaporate the water from these brines in order to recover the lithium chloride or whatever lithium salt it may be present in. So those operations take lots of time, and so you're not going to suspend operations if you're recovering lithium from brines if you're using evaporation ponds. And in that previous slide, you saw just a small picture of what some of those ponds look like. So they're going to continue to be extracting lithium from that sort of operation, but the reality is if you're crushing rock, um, when the price of the metal drops or energy costs get too high, you may suspend operations until it's viable to continue to mine. So I think it's an open question to me whether the US can produce enough lithium to satisfy future needs. And in fact, a few years ago, I remember an economic geologist speaking to a lunchtime crowd at the SME conference in the mineral processing division, saying that it's kind of crazy to be thinking that battery metals and rare earth elements actually exist in economic quantities in the United States. And so again, I guess I would argue when you looked at that global map that miners go where the metal is and where it's viable. So I see there's already some questions. Wasn't sure, I guess for water use in brine sources, can you differentiate between evaporation and direct lithium extraction? Yeah, so there are a lot of different strategies. So direct lithium extraction typically is going to require some chemical approach. And so there you're introducing another cost to your operation. So evaporation, I guess I would say there are two things about evaporation as a means to recover lithium is time, because you're probably not going to introduce energy to evaporate that water until the very end. And so that's why we see those very large evaporation ponds. And then I think, as far as I know, most of the direct approaches to lithium extraction from brine are still kind of in the developmental stages. So I'm not aware of anybody using a DLE approach for recovery from brines yet. So I don't know if that, let's see. Okay, she would like to answer this question live. Okay, so I'm not going to answer any more of these that I see. So I'll stop doing that and we'll go on to the next slide. Okay, so one of the things that we've seen in the lithium market is over the past few years since kind of the emergence of the world economy from COVID was a massive increase in the cost of lithium. And so I'll focus on the right panel here in this slide. And you're looking actually at a variety of critical minerals for batteries, but lithium is there on the left side. And these are not dollar prices, by the way, these are indexed prices. So the price of lithium carbonate in 2021 equaled 100%. And then you can see how much lithium prices increased. And I believe that wasn't too far towards the end of 2022 or 23 when we saw a massive spike um, and peak in the cost of lithium. And if I recall, that was something around the order of about $75,000 per ton of lithium carbonate. But you can see what's happened in the intervening probably year and a half maybe is that that price has plummeted. Um, and there are a number of factors that go into it. On the left side, you see the sale of electric vehicles, which this is coming from the International Energy Agency's report on global critical materials. And there's also other reports that you can find looking at battery electric vehicles and how they impact the strategy to approach net zero um, carbon emissions. That's what NZE means here. And you can see that the numbers are going up. And the last report I looked at from IEA said that if you looked at all factors considered, the one bright spot in terms of targets for NZE was the incorporation of electrification and battery electric vehicles into the equation. But you can see that there's a tapering off here between 2022 and 2023. And you have probably heard that across the globe, there has been a tapering off. And except for China, we're not really seeing um, massive growth in electric vehicles and in fact some depression. So that decrease in demand coupled with rapid expansion of um, mining and increase in supply, which is what you saw as the lithium price peaked around 2020, end of 2022 and into 2023, um, led to a lot of supply. And that didn't just impact the availability of the primary lithium carbonate, but it also was reflected in the production of refined lithium and production of batteries. So over that time, people were anticipating a big spike, and the spike was not so big in demand. And so what we're seeing at the moment is that battery metal supply, whether it's lithium or these other metals, and by the way, graphite, since it's used in the anode and is what gives rise to the black mass that you see when you recycle batteries, um, all of these things that go into batteries for electric vehicles have really plummeted in terms of their price. And so what's happening is that all the producers are ratcheting back production. And where you see this most dramatically is in Australia, where there's a lot of spodumene mined, as if you recall from that map of where the lithium is around the world. Um, and we've seen actually some mines owned by Albemarle go into what's called care and maintenance. And care and maintenance essentially means that a mine is being shut down and they'll keep a low level of activity anticipating that there may be a change in the market conditions. Sometimes it's labor, but in this case, it's definitely market conditions that would lead to turning things back on and producing the metal at the full benchmark for that particular mine. So we're definitely seeing a retraction in production, basically while miners wait for the market to respond. hopefully because we're incorporating more electric vehicles into our economies and our commerce, and making it profitable again for the mines to operate. So the mines aren't being closed, but they're basically being ramped down to basically a kind of a subsistence level. And so um, that means a lot of labor associated with those mines is also being curtailed. So it's not a great thing, but it means that there is that capacity that's sitting there waiting when the market conditions are correct. So this is probably something that most people didn't anticipate. And there's been a lot of question, particularly in Australia, about, you know, when are things going to turn around, and when are all these different metals that are also major products from Australia um, going to be viable again. So again, I'd say this was kind of not anticipated, and it shows how quickly the market can respond to rapid changes in the price of the various finished metals. So this is not a great thing when it comes to considering recycling, because if you can produce the metals through primary production at a low cost, then there's very little driver for recycling. So I'm going to talk about recycling now for a bit. And this isn't going to be a highly detailed discussion. There are lots of articles out there from many different sources if you want to get into the nitty gritty of life cycle assessments for not just lithium, but all the battery metals. And I think I first saw a talk in Germany probably in 2017, where Marcus Reuter was talking about whether it made sense to recover lithium and other metals from spent EV batteries. And at that point in time, he said it didn't make sense. Um, and I guess I'm going to approach this from a little bit different level and talk about some of the other parameters that are important, like environment, and maybe talk about this more from a perspective of the United States. I don't think we are necessarily the best example when it comes to recycling of just about anything. And some of it, I believe, is due to regulation. We certainly see a lot more regulation in the European Union for recycling. And I think a case in point is for EV batteries, that there's regulations already in place requiring 50% recycling of lithium and other metals from EV batteries by 2030, and then by 2035 an increase to as much as 80% recycling. So those are really dramatic and aggressive goals. And I guess one might argue that we don't have the technologies to do that economically yet. But here's an example of how much lithium could be recovered using either the natural resource or spent batteries. And so here you can see comparisons of cobalt and lithium. So, you know, again, we've talked a little bit about the amounts available from hard rock or brine. And so these are rough estimates from the Department of Energy. 250 tons of ore to make 1 ton of battery grade lithium, or 750 tons of brine. That's a little bit low compared to the estimate I just showed you of 1,900 tons, essentially, of the water required. But some of that water is going into the processing to make lithium carbonate. And if you were to recycle batteries, it's been estimated that it takes 28 tons of lithium-ion batteries to come up with one ton of battery grade lithium. So the US domestic volume of spent batteries is estimated to exceed 2 million tons by 2040. And so you saw that kind of growth curve in EV sales. And so these spent batteries track with that. One of the challenges for developing a recycling market is that right now there just aren't enough batteries being disposed of from EV vehicles. I've heard arguments that perhaps it's, you know, the engineering that's gone into the early EV batteries has actually been so good that the batteries are not wearing out as quickly as people thought they might. And by the way, kind of the benchmark for when a EV battery has reached its useful life for an electric vehicle is about when it starts charging at less than 80% capacity. And so that's kind of what leads to a battery being disposed of. And again, there just aren't enough batteries going into the recycling market to generate a driver for that industry in the United States. So again, where you have regulation, I think that's going to happen much faster. And we already see, I think, proliferation of recycling centers in Europe as an example because of those regulations. So when we talk about recycling, I think everybody knows I'm pretty sure that it came from Earth Day, the reduce, reuse, recycle concept. And I think every kid in the United States probably can spout that mantra. It's a good mantra. And again, I think we're probably not so good about practicing that mantra. Um, One of the people who I think has been kind of a pioneer in thinking about recycling of lithium batteries has been Linda Gaines at Argonne National Lab. And this is one of her more recent publications in recycling, talking about the Recell Center at Argonne. And this graphic comes from that paper showing the blue path, which is the primary production path, going from mining to production of finished batteries, and then various means that currently exist for recycling of electric vehicle batteries. You do see a shunt there. So there's a small shunt bypassing the red, which is basically the spent battery path. And that's reuse of these electric vehicle batteries. So something that doesn't exist in a lot of recycling streams is the potential to take that finished battery and take it and perhaps use it again in other energy storage uses. Now, one challenge to that is that you do have to go through and identify cells within those battery packs that no longer work in order to keep the battery from being a safety hazard. So I don't believe that we have a good way to do that. It's essentially a manual process at the moment. But a lot of these battery packs would be perfectly fine for energy storage use, either by consumers or going into large um, electricity storage facilities, taking renewable energy sources like wind and solar. So that's a use that I think we have to seriously consider. And it poses an energy engineering challenge to figure out how are we going to efficiently and cost effectively cycle those batteries from electric vehicle use to another use before they go through these other recycling strategies, which essentially involve taking the batteries apart and restoring them or recovering the materials. So you can see there's three major recycling strategies once you've decided that the battery no longer can be reused on its own. And those include pyrometallurgical processes, which is essentially smelting and combustion. The combustion actually can be a good thing because if you have been following some of the hazards of recycling any kind of lithium battery, the flammability of the electrolyte is often the most dangerous part of handling and storage or shipment of these batteries, whether they're new or being recycled. And of course, old batteries that are being recycled sometimes can be damaged, and so that flammable electrolyte then becomes more of a potential hazard for fires. And those fires, as you probably know, are very difficult to put out. EPA has been studying the incidence of fire associated with recycling facilities. And I'll show a graphic in a minute, but when you look at the consequences of those fires, I mean, in some cases, an entire facility is at risk if you can't get that material out of the facility to burn itself out. There's no easy way to put out those fires. Um, But if you can introduce them into a pyrometallurgical process, then you actually probably want some of that flammability because you can take advantage of the heat uh, to do your process. Of course, the downside of that is that any pyrometallurgical process is going to have a CO2 emission footprint that's probably not desirable. Other processes that can be used are hydrometallurgical processes. And I at MPC, in my one of my first slides, I highlighted some of the sessions where people are looking at how do we improve and increase the efficiency of recovering battery metals through hydrometallurgical processes like flotation concentration, for example. So you can take advantage of collectors in flotation to selectively um, concentrate some of those metals that you would like. And then finally, direct recycling, which means dismantling of the batteries and then trying to take advantage of separate waste streams that have not been commingled so that you can have a more pure product that can go into recycling. And I just read that BASF and some partners are looking to build the first fully um, uh, the first new batteries that have been assembled from direct recycling waste streams, taking advantage of the lithium and other metals and graphite that are in those batteries. So these are the three primary means of recovering these battery metals from the waste batteries. And in my next slide, I'll kind of show you some of the complexity here. So this is from a recent paper kind of summarizing. This is from ACS. The citation is there at the bottom. And so you see pyrometallurgy, basically adding other things to generate heat. Again, the flammable electrolyte can contribute to producing heat, and then you can basically smelt and recover the battery metals. So that's a very efficient but high carbon footprint approach to recovering the battery metals. Hydrometallurgy, which I just spoke to you about in terms of recent sessions at IMPC, uh, essentially you need to inactivate and then grind the batteries. And so um, there are some videos you can find out on YouTube showing that process where you throw in a cell, and it's really impressive that you can see the off-gassing of the flammable organic electrolyte, and then production essentially of a black mass that then has to be separated and go through various chemical steps to recover the various metal waste streams. And then finally, the direct method, which again requires disassembling the batteries. And so people are looking at robotics as a means to do that. Right now, a lot of labor at recycling centers in some of the test environments is probably going to be the biggest cost associated with doing that. You have to provide for the safety of those people as they're working with potentially damaged EV batteries. But if you can do that, then you can keep a relatively pure um, metal waste streams and other products, including the plastics and the housings. There's a lot of electronics that goes into these batteries, battery management systems, because there's a lot of safety that is basically controlled by electronics to keep those batteries safe if a cell fails. So that separation right now is very labor intensive. And so one has to wonder at this point, I haven't seen any life cycle assessments that actually show those costs, but it could be really interesting to see if that's going to be a viable strategy without robotics introduced into it. So again, going back to Linda Gaines' work, she looked at um, this is kind of a pseudo life cycle assessment, if you will, looking at not only the costs associated with these various approaches to recycling of EV batteries, but also energy, water, greenhouse gas, and SOx emissions. And as you might guess, the pyrometallurgical strategies might be the ones you would expect to have more greenhouse gas emissions. But if you look at this here, so pyrometallurgy is in blue, see if I get this right. No, it's in green, sorry. Um, Hydrometallurgical approaches are in yellow, and then direct approaches are in this gray color here. So overall cost, so compared to direct mining and production of the metals, you can see that the pyrometallurgical approach is more expensive based on her analysis. Hydrometallurgical overall, almost 100% of that cost. And then the direct approach turns out to be a much less expensive approach. And it makes some sense because you can keep, you're not commingling and then having to separate out all the metal components again. If you look at energy consumption, you can see that there are cost savings for all these approaches compared to direct production of the metals. Water consumption, again, quite a bit of savings. Greenhouse gas emissions, here's where we get into some of these approaches like pyrometallurgy are potentially emitting as much or close to as much greenhouse gas as you would by the direct production. And again, the big winner is direct recovery of the battery metal components. And then SOx emissions, primarily probably from energy production required in mining. And there's still a lot of energy produced around the world that's not coming from clean sources. And then surprisingly, SOx, probably because we have scrubbers on a lot of our pyrometallurgical smelting applications, is not really emitting that much. And then I don't recall at the moment what was the factor that led to the higher SOx emissions from the hydrometallurgical applications. And then just very briefly showing this again, safety is something that I think you have to always keep in mind in terms of the recycling of these lithium batteries. And you can see that in this report from 2021, lithium batteries accounted for 40% of fires at waste management facilities. And one thing I've learned in talking to colleagues in Australia and Canada is that this is becoming a challenge for those countries in terms of not only shipping of collected lithium batteries, but storage of those batteries and handling. And in some cases, different provinces in Canada, for example, are banning the disposal of lithium-ion batteries. And some companies that we work with in the mining industry are ending up with hundreds of tons of lithium-ion batteries that they, at this point in time, have no way to dispose of. So it's becoming a challenge just from the handling and safety perspectives, let alone when we look at what are the costs associated with these batteries. So one thing I wanted to point out is that if you think about what are the big differences between lead acid batteries that we can recycle now compared to lithium-ion batteries, form factor is a big one. But form factor alone isn't the only question. It's all of the additional things. You can see the battery management systems that are connected with these lithium-ion cells from an automobile electric vehicle battery. And you can see the individual cells. So there are a lot of these individual cells that go into making an automobile battery. And I think I've seen estimates that the number of cells in a Tesla battery is something on the order of about 7,000 cells. So another engineering challenge beyond the recycling strategies is there a different form factor that we can come up with that would make recycling more effective? Is there a way of dealing with collection and storage of depleted batteries that would make it less hazardous and safer for these facilities as they operate? But right now, I think we're still in a time of churn where there's a lot of changes in chemistry. Everyone's going towards safer chemistries, more efficient chemistries, increasing the storage density of the batteries. And so I think it's very difficult right now to think about how you would come up with a strategy to come up with a uniform form factor. But I think when you look at the success of lead acid batteries, where 98% of our lead acid batteries, that includes acid gel mat and gel batteries, are recycled, that's a real success story. And I think we need to think about how can we transfer that, the learnings from that to EV batteries. So I'd like to end just with a few questions. Um, what is the solution for the United States? And so our article was written from the National Academy of Engineering perspective on, how do we solve these challenges for the United States? I think the one thing that's clear is right now, free market drivers aren't likely to be the way to increase recycling or to come up with economic ways to um, come up with efficient modes of recycling. One strategy that may work is that there are automobile manufacturers who are considered closed cycle recycling. So they would take back the EV battery and ultimately figure out how to return the metal values into new EV batteries. Safety, I think, is a critical issue. I think because we're hearing of restrictions around the world, you already know as travelers in US air or international air travel, you need to be carrying your own lithium-ion batteries, even if they're small, laptop size batteries. And there are lots of restrictions on how bigger batteries move around in cargo transport, whether it's in the air or on the sea or in trucks. So we really need to be pushing for safer chemistries. Lithium iron phosphate seems to be one safer chemistry, but it's a trade-off with a lower energy storage density. And then one that I know is not popular in the United States, but can increase regulation and financial incentives from the government, drive sufficient recycling so that we can be competitive on a global scale with other countries, and ultimately because it is a global market for these metals. So I'll stop there. I know that I'm a little bit over time and take questions.
First, Dr. Roberto, I'd like to thank you for a great presentation. This is like a thought paper, a thought presentation where you've shared with us lithium-ion battery life cycles and really the environmental, economic, and safety issues also with those with regard to everything that needs to be considered in safely recycling lithium batteries as well. So a lot of big issues here, and we have a great group of questions. So again, thank you so much for the presentation. And let's begin with Linda's first question here.
Okay, I'm seeing before
Oh,
Linda, I
let me
see
see if there, yeah. Oh,
Herman
yeah.
Liebet had a question. So is lithium price an open market pricing?
Oh,
It is. So it is very sensitive to um, the market, and that's why we're seeing this dramatic change. I don't think I've seen, except maybe in the gold market, I haven't seen such a dramatic change. And it's not just lithium, if you recall from that IEA plot of other battery metals.
now a
Linda
question
Gaines,
for me.
yeah, Linda's comment. Really, I agree with you wholeheartedly, Linda. I think the best estimates I've seen is that maybe recycling can supply 10% of our demand. And I'm thinking about it again more holistically. So I think it's not just economics. I think we need other drivers to push recycling and circular economy, at least the way we look at um, free market economies right now. And so I don't know what the answer is. I've proposed a few things, and I know some of them are not popular, but I do think we need other things to drive recycling. Next question: direct recycling has application limitations and has not been commercialized yet. Certainly true, and I think again I pointed out that from my perspective, the labor costs alone um, could make it difficult to see direct recycling um, be viable. Uh, Another comment from the same question. It may be a solution for some applications, but will be difficult for AOL batteries, end-of-life batteries. I think that's certainly true. Is the solid-state battery versus LiB technology the future? I don't know. I think that it certainly could lead to reduced safety issues, but there'll be higher metal requirements for those solid state batteries from my scene. Sodium batteries are another potential alternative. I've heard that as long as lithium prices stay low like they are now, that sodium's not going to be a viable alternative, but who knows? I certainly think we need to continue to innovate in terms of battery chemistries, but I think it needs to be done in the context of what's the form factor that would lead to a way to recover those metals or eliminate the hazards of those metals, if nothing else. Um, Recycling can't supply much of our demand until growth has been stopped for a while. I guess that's already a comment, I think. Could the U.S. impose a core charge on recycled batteries similar to the lead acid battery processing? That's a good question. And I think, again, the whole reason for putting that comparison of the lead acid success story compared to, I think, the heterogeneity we see in lithium-ion batteries for not just EVs, but computing, power tools, hand tools. I think we do need to consider other drivers that could lead to more recycling. And it's a difficult challenge because I think if I think about the United States, I know that the state of California, because they're likely to be the biggest holder of EV batteries, whether it's in vehicles or in recycling, is already thinking about what those solutions might be. I think we do need to consider other ways to incentivize recycling. How does the lifespan of directly recycled batteries compare to new batteries? There aren't any, so I think it's very difficult to say what they might be. I guess we'll see. BASF is going to build one or build a facility to build them. I know that there are some challenges because you actually have to regenerate the lithium so that it will store the amount of power that it did before the battery was depleted. So there are definitely going to be some challenges there.
I think that might be the end of our questions at this point, but I do have, oops. Sorry about that, technical difficulty there. I want to thank everybody for coming to this webinar today, and would like to remind you that you can see this in a week at the Critical Materials Innovation Hub YouTube channel. And I'd like to have you join us for the next webinar as well. And that is I have to apologize for keep losing our slide here. And our next webinar will be listed in the Critical Times as well. And I'll look forward to seeing you this upcoming month. So thank you again. And Dr. Roberto, I think you have one more question. Nope, that's it. You have all the questions answered. Thank you again for a great presentation. And I look to seeing everybody this upcoming month.
Thanks, Cynthia, and thanks to CMI and Maureen Allen, who is in the background helping coordinate the presentation. So, and thanks
You
to
are
our audience
welcome.
for coming today.